Hey everybody, welcome back to another installment of our Intro to Music Technology course. I'm Dr. Brandon Vaccaro. I'm an associate teaching professor of music at the University of Massachusetts Lowell, where I coordinate our sound recording technology program. Today we're going to move forward with the topic of microphones. Now, for SRT majors, this is the very first time that we'll talk about microphones, but it absolutely will not be the last. In fact, a good portion of your four-year degree program will be coming back to this topic and going in deeper and deeper and deeper, both in terms of the underlying theory and construction of microphones, as well as meaningful real-world practices. However, we're just going to get our feet wet with the topic this time and make sure we have enough information that everybody, including non-SRT majors, have the background they need to be able to use microphones within their curriculum here at the University of Massachusetts Lowell in the Department of Music. So we want to begin with a consideration of microphones in general. What is a microphone? Well, on a basic level, microphones are transducers. A transducer is something that converts energy in one form into energy in another. And in the case of a microphone, the transducer is going to convert energy in the form of acoustic energy into energy as an electrical signal. That electrical signal we can then use to do all kinds of things with. We could record it by converting it into changes in magnetic flux level and put that on tape, something that's not super common anymore, but we still do that here at UMass Lowell. And we could conversely go through an analog to digital converter, turn it into digital information that could be stored in a computer using a digital audio workstation like the system behind me. So we're going to talk about a microphone from a couple of different standpoints. And in many ways, one of the things that we can think about is microphones are sort of the opposite of a loudspeaker. A loudspeaker takes energy in an electrical form and it converts it back into acoustic energy. So if we were to look at, for example, there's a loudspeaker right back here behind my head. There it is. The various drivers on that speaker take an electrical signal and convert it into an acoustic form. So microphones are going to do the exact opposite of that. They're going to take sound in an acoustic form and get it into an electrical form that we can then use to record. So there's a couple of common construction features that we'll talk about with all microphones, and these are one of the ways that we can describe microphones by describing these construction features. So, for example, a microphone will have a capsule. That's the element that really does the act of transduction. We'll talk about some different capsule designs as we move forward through the slideshow today. Additionally, microphones will have a body or housing that usually contains the capsule as well as any electronics that's needed for the microphone. Most microphones, though not all, will have a grill that protects the capsule. And finally, microphones can be designed to be something called front address or side address, and we can talk about that very briefly right now. So I'm holding in my hand a Shure SM57 microphone. This microphone is what we call front address. We speak into it this way. The sort of action end of the microphone is here, and the diaphragm runs perpendicular to the body of the microphone. So the diaphragm is meant to move this direction. We could contrast that with a side address mic, like this Rode NT1A. This microphone, if we speak into it this way, we wouldn't get very good results because the diaphragm is actually going this way in the microphone. It's meant to move back and forth this direction as we're speaking into the microphone. We also have a couple of confusing microphones. This one looks like it would be a side address microphone, but it's not. It's a front address microphone. This is a Sennheiser MD421. We'll talk a little bit more about a few of these microphones as we get into the lecture here. So there are two basic operating principles that come into play, and they end up manifesting in three basic designs. We're not going to get too bogged down in the details. Again, this is an area where SRT majors can look forward to future classes going into much more detail about this. In this class, we just really want to learn these three basic types of microphones, and then we're going to learn some of the characteristics of those microphones. So the first type of microphone that we're going to talk about today is based on something called electromagnetic induction. Now, the first type of microphone we want to talk about has a couple of different names. The most common name in modern parlance is a dynamic microphone. These are also sometimes known as moving coil microphones or dynamic moving coil microphones. One of the examples that I held up a minute ago, the Shure SM57. This is a dynamic or moving coil microphone. Based on a similar principle, but using some different capsule designs, we have something called a ribbon microphone. Now, because it's based on this same underlying electromagnetic principle, some people call it a dynamic ribbon microphone. That's a little less common these days. We usually just call them ribbon microphones, and we call moving coil or dynamic moving coil microphones dynamic microphones. If you just hear someone say dynamic microphone, it's probably safe to assume they're referring to a moving coil. If they say ribbon, we know they're talking about a ribbon or a dynamic ribbon. The other underlying principle that comes into microphone design is something called the electrostatic principle. Again, we're not going to get bogged down in the details with this at this stage for Intro to Music Tech. These are topics we'll come back to. However, the most common microphone built on this principle is called a condenser microphone. This is the term we use in the United States. In the UK, they commonly will call this microphone a capacitor microphone. This is one of those weird little confusing things that I have no idea how this happened. In the United States, we have an electronic component that we call the capacitor. Microphones based on the underlying principle of capacitance are called condenser microphones. In the UK and other Commonwealth countries, they regularly call these that electronic component a condenser, and they call microphones based on it a capacitor. I got no idea how that happened, but it is kind of one of those hilarious things that happens in the world of audio, and we're all sort of stuck with it. So I've got a video in the slideshow. I'm not going to show it to you here, but I do encourage you on your own time from the class link. You'll be able to get to that two operating principles video if you want to dig a little deeper into this. Again, definitely not necessary at this level of an Intro to Music Technology course. So the first category of microphones we're going to talk about, again, these are based on electromagnetic induction. In really simple terms, what happens is we put a piece of metal that can conduct electricity, and we place that in a magnetic field. When that piece of metal moves back and forth through the magnetic field, the electrons in that piece of metal will flow one direction or the other depending on the magnetic field, and that motion of electrons back and forth is electrical signal. So the principle of this involves having some pieces of metal that are going to move through a magnetic field. The first of these that we're going to talk about is, again, the dynamic or the moving coil microphone. So the capsule in a dynamic microphone is pretty basic. It's going to have a diaphragm, which is a thin material that will move back and forth in response to changes in sound pressure level. And that diaphragm is going to be directly connected to a coil of wire, so that when the diaphragm moves back and forth, it'll cause the coil of wire to move around in a magnetic field. That'll induce a current in that coil of wire. That current moving back and forth becomes our signal, and that's how we're going to get from energy in the acoustic domain into energy in the electrical domain. So we'll talk about phantom power in a minute. Phantom power, as many of you who have ever worked with a mixer know, there's something called phantom power. It's important to know phantom power doesn't impact dynamic microphones. It won't damage them. They don't require it. There's no underlying principle that requires the use of phantom power for a dynamic microphone. Some of the characteristics, some of the pros of a dynamic microphone: they're rugged, and they're usually capable of handling relatively high sound pressure level. In fact, of the microphone types we'll talk about today, on a consistent basis, we would say dynamic microphones are probably most capable of handling high SPL. However, because of the inertia issue, they have a relatively slow response to sound. When sound first arrives and interacts with the diaphragm, it takes the diaphragm a minute to start moving back and forth. And the reason for that is because of the mass of that coil of wire. There's a certain amount of inertia to get it moving back and forth, to get it oscillating in response to the changes in sound pressure level. That inertia we could say it has a slow response time. And when we translate that to some of the acoustic and psychoacoustic terms from our previous lecture, we talked about the dynamic envelope of sound, and this being an aspect of timbre. So this slow response can have a very subtle, though important, influence on the timbre of the sounds that we record through those microphones. So some examples of dynamic microphones, some common ones that we run into in the field would be the Shure SM57 and the SM58, the Sennheiser MD421, and the EV RE20. The RE20 is a microphone you see all the time, whether you've recognized it or not. It's probably the most common microphone used by broadcasters and podcasters. So you see it on a lot of podcast videos. It's the microphone that people prefer to use for that. As is typical with most of the dynamic moving coil microphones, they have relatively low handling noise, so these make great microphones on stage. They're also great, as I mentioned, for on-air personalities, podcasters that might be moving their microphone around quite a bit while they're speaking. And having something that has relatively low handling noise means we don't get a lot of rumble on the microphone. And again, this is an SM57. This is a very common dynamic microphone. We tend to use this one for miking instruments. And its cousin, the SM58, I don't have one of those handy here. They look very similar. The body is in fact identical, but they have a round, slightly different grill that encompasses the capsule. See, I also have a Sennheiser MD421. Again, this one kind of looks like a side address mic, but it is not. It is actually a front address mic. I'm not sure if I can get enough of a shadow through there that you can kind of see there. You can kind of see the little round piece in the middle, about that height where my finger is, and that's the dynamic moving coil that's going to move back and forth this direction in sound coming on axis on the microphone. So I've got a slide here that demonstrates the underlying principle a little bit. So again, inside the microphone, we would have a diaphragm, usually a thin piece of plastic or some other kind of polymer. I guess all plastic is a polymer, but some kind of plastic. And attached to it, and coming around this magnet in the center here, is a coil of wire. As the diaphragm moves, it's going to drag this coil of wire, or move this coil of wire hopefully smoothly. It shouldn't be dragging it. Should hopefully be moving that coil of wire smoothly around the magnet. And as the coil of wire cuts across the magnetic flux lines of the magnet, that'll induce a current in the coil of wire, and that change in current should correlate pretty closely to the change in position, or rather the velocity of the diaphragm. So that's a good cross-section of a dynamic microphone. So next up, we want to talk about ribbon microphones. Again, these are sometimes called dynamic ribbon microphones. So with a dynamic ribbon or a ribbon microphone, we have the same underlying principle. We're going to have a piece of ribbon, and that ribbon is placed in a magnetic field. The key difference between a moving coil microphone and a ribbon microphone is that in the case of a moving coil microphone, we have a separate diaphragm and a coil coming off of it. In the case of a ribbon microphone, the ribbon itself is the diaphragm. So the response is going to be a little different, the behavior is a little different, and the construction obviously is quite a bit different. So in the case of a ribbon microphone, we usually have a very thin piece of metal that's actually usually corrugated. It's folded so that it has a lot of surface area, it has some flexibility, and it moves back and forth through a magnetic field, and that induces a current flow. Generally, these have a pretty low output signal compared to other type of microphones. So often they're going to need some additional internal electronics, including a step-up transformer, to get them up to a more normal microphone signal level. And we'll talk a little bit about microphone signal level at the end of this slideshow. So with ribbon microphones, just like with moving coil microphones, we have no need for phantom power. Phantom power is not required for the underlying operation of most ribbon microphones. We'll come back to that caveat in a minute. However, it is important to understand that many ribbon microphones can be destroyed by phantom power, and this is particularly true with older vintage ribbon microphones. So it is really important, probably more so than with any other microphone type, to make sure that you've familiarized yourself with the specifications and characteristics of a ribbon microphone before you ever think about plugging it in. Again, some ribbon microphones can be destroyed by phantom power. There is a special category of ribbon microphones that we call active ribbons. These microphones have amplifiers built into the body of the microphone. So that component, those amplifiers, require active power, and there's some electronics in the microphone that will prevent the microphone from being damaged by that phantom power. In that case, that microphone will actually not work without phantom power. So again, it's a little bit confusing because a ribbon microphone could be impervious to phantom power, pretty indifferent to it if it was built in that way. It could require phantom power, but in some cases, it could be destroyed by phantom power. So again, it's really imperative that you look up the information on this on any of the ribbon microphones that you might use before you connect them, before you think about powering up phantom power. So ribbon microphones have a moderate to fast response, and the reason for that is because we've eliminated all of the extra weight that was in the moving coil. We have a much lighter system and consequently a lot less inertia to get the system going. Most ribbon microphones can only handle low to moderate sound pressure level. Now again, just like with phantom power, this can be a little confusing because there are some modern ribbon microphones that are capable of handling very high SPL or relatively high SPL. Probably not as high as most moving coil microphones, but again, there are some that are capable of handling high SPL. However, do not assume that your ribbon microphone, or really any microphone, is capable of handling very high SPL until you've gone, looked up the specifications, and made sure before you put it in front of a really loud sound source that could potentially damage your microphone, that it's actually capable of handling the kind of sound pressure levels that it's going to encounter in that particular location and application. So some examples of ribbon microphones would be the Royer 121. This is a really common microphone that many of us use to record electric guitar. I'm quite fond of the 121 on guitar amplifiers for clean guitar sounds. It has a cousin, which I believe is called the Royer R122, which is an active microphone. For those of you who are SRT students here at UMass Lowell, that is a microphone that we have in our microphone locker and one that you will certainly have a chance to work with in more advanced classes. Again, that is an active ribbon microphone, so it is one that would need phantom power to function, as opposed to the 121, which is a passive microphone. Some other options would be the Beyerdynamic M130 and M160s. These are microphones that are moderately affordable. They're on the expensive side as far as microphones go, but not as far as ribbon microphones go. Ribbon microphones can be quite expensive. The 160 and 130, the nice thing about them is one of them is a figure of 8 microphone, which is something we'll talk about in a few moments. The other one is a cardioid microphone. So SRT students will learn in some future applications that we can combine those two microphones into a stereo pair known as a mid-side. So that's really kind of a cool thing to have a ribbon microphone mid-side pair. On the vintage side, an RCA 44 would be a classic ribbon microphone. In fact, one might say this would be kind of the archetype for a lot of our pictures of microphones going back to the 40s and 50s. So here we see a cross-section of a ribbon microphone. And again, just like with the moving coil microphone, we have a magnet, in this case a U-shaped magnet, and in between we have that corrugated ribbon. Again, it's folded many, many times. And that itself is actually directly wired to, in this case, a step-up transformer to increase the output and provide the appropriate impedance for circuitry downstream from this microphone. So finally, we want to talk about the third type of microphone that we're going to talk about in this portion of our lecture. This one is based on a different principle. This one is based on something called the electrostatic principle. So before, we had a piece of metal that was moving back and forth through a magnetic field. Now, with this type of microphone, we're going to have something a little bit different. We're going to have two plates, two conductive plates of material that are kept some distance apart. Now, the distance we're talking about usually, these are in the millimeters, in the millimeter range. These are very close together. But these two charged plates, one of them is charged positively and one of them is charged negatively. Between them, we have a property called capacitance. Now, one of those plates is mounted so that it can easily move. It's the diaphragm of the microphone. And as the distance between those two plates change, we're going to change the capacitance of the circuit, which causes current to flow, which is what our signal is going to be based on, is that flow of current and the related concept of voltage. So the microphone we're talking about here, again, these are condenser microphones. Now, a true condenser microphone needs something called phantom power to operate. And this is because we have to pre-charge those plates. In order to build up a charge and a difference in charge between those two plates, we need to provide that charge from somewhere. In modern electronics and in modern audio equipment, we generally provide that with something called phantom power. It's called phantom power because we send that power signal over the same cable that we run our audio signal through. And this is generally going to be provided as a DC voltage, a positive DC voltage. Modern range, you see ranges from 12 volt DC up to about 52 volt DC. The standard for modern microphones for the last 30 years plus has been plus 48 volt DC. And some microphones are very sensitive. They need that plus 48 volt precisely. Some microphones have a variance and they simply perform a little out of spec if our phantom power is a little off. Ideally, we want quality equipment that provides a really good phantom power source for our microphones. So, generally speaking, condenser microphones are going to have a wide, smooth, and a very fast response. They can be built to handle high sound pressure level. However, we tend to think of them as really excelling in scenarios where we have a lot of low sound pressure level signal or a very broad dynamic range. SRT majors will learn in later classes that generally condenser microphones ideally have relatively low self-noise. And that means the background noise from the microphone is low enough that we can record very, very, very low and quiet signals. So these are often the microphones that we would pick and choose if we were going to record acoustic instruments, especially acoustic instruments with a really big dynamic range. So, some examples of this include the Neumann U87 and the TLM49, the AKG 414. There are many, many, many more out there, and in my props table here, I have a Rode NT1A. This is a microphone SRT majors will, again, like all the ones I'm demoing today, these are things that you'll likely be using in some of the upcoming classes. This is what we call a large diaphragm condenser because the diaphragm is relatively large. I believe it's in the 3/4 or 1 inch range on this microphone. And here I have a Rode NT5. This is what we would call a small diaphragm condenser. You can tell from the diameter of the body and the housing that this is quite a bit smaller than the diaphragm on this NT1A. So this would be regularly called a small diaphragm condenser, sometimes abbreviated as SDC. Large diaphragm condenser, sometimes abbreviated as LDC. So here we have a cross section of a condenser mic, and we can see here we have the front and the back plate. Again, the front plate is also known as the diaphragm. It's the part that's going to move in response to sound pressure level changes. The distance between those changes the capacitance of the circuit, which induces our signal. Here they're showing the phantom power is coming from a battery supply. This is not uncommon. It's also not super common. This would be a common application in a lot of portable devices like your phone. However, in most professional audio equipment like we would be using to record music, we would provide phantom power from the microphone preamplifier that would come over the same cable that our signal is traveling through. So a couple other properties we want to talk about with microphones. These are properties that we can apply to all microphones. And if we were going to describe a microphone, these are some of the terms that we might use after we've specified whether it's a dynamic mic, a ribbon mic, or a condenser mic. So the first property we want to talk about is something called directionality. Directionality describes how a microphone responds to sound coming from different directions. Grab my SM57. What we're talking about is the way that the microphone responds from sound coming from this direction versus sound coming from this direction, or this direction, any other direction. Additionally, we want to talk about something called frequency response. Frequency response is going to be the range of frequencies that a microphone will react to, and it includes the balance or the response throughout that range. And so ideally this is shown on something called a frequency response graph. So let's look at a couple examples of the ways that we might indicate these directionality characteristics or the frequency response characteristics. So on this slide, we can see the polar response pattern for something called an omnidirectional microphone. An omnidirectional microphone, as the name implies, responds to all directions equally. So this chart isn't the easiest for us to understand right now because we don't have anything to compare it to. But to describe how this works, we have the front of the microphone up here labeled as 0 degrees. Some manufacturers will put the 0 degrees at the bottom. Doesn't really matter as long as we understand that this is the forward bias on the microphone. So if we were talking about the Shure SM57, 0 degrees would be sound coming from this direction. Again, 0 degrees, that's going to be sound coming from this direction here. So as we move off axis, 30, 60, 90 degrees, we notice that this heavy line follows the outer circle, which is labeled as 0. What that means is that we're going to have a 0 decibel difference between sound at the 0 degree point and sound at the 90 degree point, or at the 180 point, or at the 270 point. Again, what this is showing us is that sound coming from any direction of this microphone will get the same output signal level. We can contrast that with the next slide here. On this one, we can see something called a bidirectional mic, or a figure of 8, or sometimes just called a figure 8 microphone. So here we have sound, or this is the on-axis response, the 0 degree point here. And we find as we start going off axis, the signal starts deviating from that 0 line and goes down towards the -5, -10 line eventually, and makes its way down until here at 90 degrees and at 270 degrees, we get what are called nulls. In theory, if we were perfectly at 90 degrees with this microphone, we would get absolutely no signal level at all. Any other point, at any other angle from the microphone, we will get a lower output signal than we did when we were right at the 0 degree point. Now, if we keep going around past 90 degrees, we see that this pattern, this lobe on the front half of the microphone, repeats exactly, and that gives us our figure of 8 shape. Again, this is a bidirectional microphone, so it will respond equally to sound from this direction or from this direction down here. We can contrast that with this slide, which shows a unidirectional microphone. It's only going to respond from sound in one direction. Here, as we begin to move off axis from the microphone, we find that the signal again starts to attenuate, but rather than dipping to a null at 90 degrees, this microphone type, which we call a cardioid, goes to a null at 180 degrees. In other words, Sound coming from this direction is going to respond at a certain signal level, but again, sound coming from this direction in theory would completely not respond to the microphone, or rather the microphone would not respond to sound, rather, coming from this direction. And again, any other angle, we're going to get an attenuated output compared to the on-axis response. So it's important to remember this slide shows an SM58. I believe this is a slide from Shure's website that shows how this cardioid microphone shape, this unidirectional microphone shape around an SM58 goes in 3 dimensions. It's important to remember we represent this with a 2D drawing like we see right here with this cardioid shape, but in reality it's 3 dimensions all around the capsule of the microphone. And again, this directional property is something that's really important for us. In practice, the way we might use that is if I have a couple of microphones in the same room and I'm recording multiple instruments with different microphones, I might not want to have the signal level from one instrument end up bleeding into the microphone from another instrument. And one of the ways that we can minimize that is by utilizing those nulls. So for example, if I were recording a singer-guitarist who sings and plays guitar at the same time, I'm going to have a microphone on their voice, I'm going to have a microphone on their guitar. If I can selectively use microphones and place it so that their mouth is in the null on a microphone that's miking the guitar, and the guitar is in a null on the microphone that's miking their voice, I'm going to get a lot less crosstalk between those microphones, which gives me some advantages when it comes time to mix that signal and get the final mix done on that recording. So here we see a couple of secondary patterns, and we call these secondary patterns because they're sort of the result of combining some of the previous patterns that we've seen. So we can see this kind of looks like it's a bidirectional mic, but we've shrunk the rear lobe. And in doing so, we shifted those nulls from 90 and 270 degrees out a little bit wider when looked at from the front. Now the front lobe has a little bit of a cardioid shape to it. So we can kind of see this as a combination of a cardioid and a bidirectional microphone. And incidentally, we call this particular pattern hypercardioid. This is a pretty common microphone diaphragm type. I think in a lot of directional microphones, we will regularly see cardioid and hypercardioid. And here we see a supercardioid. Again, similar in that we've got a cardioid combined with a bidirectional shape. And if we really look at this rear lobe, it's so much smaller than in the previous slides compared to a bidirectional, hypercardioid, supercardioid. And in doing so, that usually tends to widen out the cardioid shape on the forward lobe, on the front lobe, and obviously attenuates the rear lobe quite a bit. It also pulls those nulls a little farther towards the 180 degree point, though obviously nowhere near 180 degrees, but a little bit wider than what we had here and quite a bit wider than what we had in our bidirectional. There's a couple other polar patterns that are a little less common, and we don't run into them very often in the world of music. Probably the most common of them is something called a cancellation tube mic. These are also sometimes called shotgun mics. Now, a shotgun mic, probably the most common application where we see shotgun mics are in the world of film and television when we're shooting video. And they're regularly attached to something called a boom pull, which a boom op will then stick that pull out over the talent, slightly out of the screen. In fact, my voice right now, you're hearing me recorded through a shotgun mic that's a little bit above the camera, right up there. And again, they tend to be used in scenarios where we want a very, very, very directional sound source that allows us to record, for example, in this case, my voice, while capturing very little of the computer noise that's happening around me in this room. On a set, obviously that can be really important because there can be a lot of things happening on set that can make a lot of noise, ranging from smoke machines, special effects, crew moving around, moving cameras, changing things on set, all kinds of things that can be generating a lot of noise. Additionally, there's something called a boundary mic. These are also sometimes called pressure zone mics or PZMs. That was actually a trade name for the company that first designed these, a company called Crown. They had a patent on them for many years. Their patent now expired, and there's a lot of companies that make these. Pressure zone mics are designed to be placed at the perimeters of spaces. So we might imagine a scenario where we could put them on the surface of the wall in a room. Another application that I see people use them a lot, especially for live sound, is on the interior of a grand piano, where they're right up against the surface of the grand piano at a point that we call the pressure zone. These are designed to work in situations where regular mics, particularly pressure gradient microphones, don't excel very close to the surfaces of a space or a room. Let's move on now. Let's talk about frequency response. So frequency response can be given in two forms. One is something that we call a frequency range. So for example, if you look in the specification sheet for the Shure SM57, you'll see that its range is from 40 hertz to 15,000 hertz or 15 kilohertz. Now, that doesn't tell us anything about how the different frequencies across that range will react in terms of that microphone. Or rather, again, let me flip that around. It doesn't tell us anything about how the microphone will respond differently to frequencies across that range. For that information, we prefer to see what's called a frequency response graph. And this will be a chart that will show the responsiveness of a microphone from low frequencies to high frequencies. Here on the left-hand side of the screen, we can see the polar response charts for an SM57. Now, one of the things we want to notice is when we talked about this earlier, we simply saw one shape. Here, we're seeing several different shapes, and if we look at the legend below, we can see that these different types of lines are indicating different frequencies. In other words, at some frequencies, this microphone is a cardioid. Again, notice 0 degrees is pointed down here in the Shure charts. So this is a very cardioid microphone at certain frequencies. At other frequencies, it kind of comes off not quite cardioid-like. We don't really have a null on the rear here at this very low frequency point, which I believe in the legend is maybe 125 hertz. We actually get kind of a squished omnidirectional response. And as we go over here into the high frequencies, and higher frequencies rather, we can see that it stays somewhat cardioid-like, but we get some interesting effects that happen towards the rear null here, where it doesn't quite act as a null. Again, this is only to indicate that real-world microphones, do not have a singular polar response. Their polar response will vary depending on the frequency of its input. Now, in terms of frequency response chart, we can see the SM57. You'll recall from the previous slide, I said this went from 40 hertz up to 15 kilohertz, and we can see that shown with the heavy line in the middle here. Now, the way we want to read this, these are always placed so that 1 kilohertz or 1000 hertz happens at the 0 dB line. And if the microphone will respond with a higher output to a particular frequency, it's shown here going up above that 0 dB line. If the microphone produces a lower output than 1K at that particular frequency, the line goes below. And what we see here is this from going up from 1 kilohertz, starting at about 2 kilohertz and going up to 7, 8K, we really get this kind of interesting spike that happens here where we get a higher output in this frequency range than we did at 1K. And then as we start to approach the top end of the microphone, it rolls off and we actually get a lower output than we did at 1K. We stay relatively flat going down until we get to about 400 or 500 hertz and we get this little dip. Then as we move into the low frequency range, we can see this rolls off quite a bit, in fact, quite precipitously. By that 40 hertz tone, or that 40 hertz frequency range they gave us for the bottom end of the frequency range, we can see that we're actually down by a little over 10 dB. If I recall correctly, it's about 12 dB down at 40 hertz. So it's definitely a significant drop-off in the responsiveness at 40 hertz. Now, we might imagine, as we're looking at this microphone, that since it doesn't respond equally at all frequencies, that could be a bad thing. In reality, that's not really true. It's just a characteristic of the microphone. There are times where we in fact want a microphone that represents all frequencies equally. There's also times that we want a microphone that exaggerates certain frequencies. We can think about the responsiveness as the microphone as sort of having an EQ on the microphone. And if we're going to end up EQing and boosting certain frequencies when we record or when we're playing back through a sound reinforcement system, why not use a microphone that does that for us at the capsule or sort of within the signal flow of the microphone. So here we can see the another way of representing the polar response charts that we were seeing here. Again, if we pick any angle, if we pick our 0-degree angle, we get this frequency response that we see on the right side. But if we pick any other angle, we're going to get a different frequency response. And on this next slide, we see that represented on the same chart. So what we're seeing here is the sound of an SM58, slightly different microphone, so a slightly different frequency response than the SM57. But we can see here on the lower half, the same microphone with a frequency response at 150 degrees off axis. We can see it's a very, very different frequency response. And this is just showing us the same kind of information that we saw here on the left side, where we see different polar responses at different frequencies. Now, on this slide, we see something very different. This is some information from an Earthworks microphone called the M30. This is an acoustic measurement microphone, so this is designed to be a very, very flat microphone. So if we look at the frequency response on the right side, first off, we want to notice that the legend actually, rather than going up by 5 decibels at a time, is now only going up by 3 decibels at a time. In other words, we've sort of zoomed in on the y-axis here. And yet we see this microphone is responding very equally across the entire frequency range. And when we look at this, this is what we would call a flat microphone. When somebody says they're using a flat microphone, what they mean is a microphone that has a very flat frequency response when represented this way. We can also see that this microphone actually responds to much lower frequencies than the SM57 we were just looking at. In fact, it's pretty much flat down to about 10 hertz and then rolls off only by about 3 dB to probably 7 or 8 hertz below that. As we go to the high end, we find it stays very flat up to about 20 hertz and then rolls off down to about 30, by about 30 kilohertz, it's still relatively flat, and we can see it drops off after that. In fact, the 30 in the M30 refers to that 30 kilohertz high end. They have an M23, they have an M30, and they have an M50. The number and the model number tells you the high frequency range that it responds to. Looking on the left-hand side, we can see the polar response chart, and we can see this microphone is almost a perfect omnidirectional microphone. Even looking at the different frequency ranges, it does become ever so slightly directional as we get into the very high frequency range, but it's still very minor. This is a very nearly perfect omnidirectional microphone. So a relatively uncommon thing. Now again, I mentioned a moment ago that there are times where we might want to choose a microphone that's got a very altered frequency response, something that gives us an exaggerated sense of certain frequencies. Other times we might want a very flat frequency response. For example, if I'm going to record a string quartet in a phenomenal concert hall, the real-world acoustic sound of that environment is incredible, and ideally I might want to capture it with a very flat microphone so that I'm able to capture all of the characteristics of that performance very much how I'm going to hear it in the hall. Other times, if I'm placing a microphone in front of a guitar amplifier, for example, or maybe placing one very close to a drum, I might actually want to use one that's got a very exaggerated frequency response in certain ranges. So again, we want to think about this not as being a good thing or a bad thing until we know what our application is, and then it might become good or bad based on the context. Another property we want to talk about with microphones, and this is something that applies to directional microphones, is something called the proximity effect. Now, in the UK, by the way, this is called bass tip-up. We use a textbook in some of the SRT classes that was written by a UK author, so I always like to mention the UK terms since you might come across them in texts or on the AES website. So proximity effect is a property of directional microphones. It generally doesn't happen with true omnidirectional microphones, tends to happen with bidirectional or unidirectional microphones. And this is a characteristic of microphones where sound close to the microphone produces an increase in low frequency on the output signal. In other words, as we get close to the microphone, we end up with more bass than we do if we're a little bit farther away. This is caused specifically by the way that we make omnidirectional microphones to become directional, so it is something that's characteristic of that. And typically, what we're thinking about with this is usually within about 18 inches or less of the microphone. So if I had a Shure SM57 and I'm very close to the microphone like this, about 6-8 inches away from the microphone, this is probably going to exhibit proximity effect. If I take the same microphone though, and I move it maybe back 2 feet or so, we're going to find if it does exhibit any proximity effect, it's significantly less than it was when it was much closer to me. Now again, we could think of this, is this a good thing or a bad thing? Well, it's just a thing. It's a characteristic of microphones, and it's something we want to take into account when we think about placing a microphone. So if I'm recording a vocalist and I know I've got somebody that sings very delicately, like a classic jazz crooner, they're going to sing very quietly like this. And I'm going to want them very close to the microphone, and it's going to exaggerate that low-end response from their voice. That's an essential part of that crooner sound. Likewise, if I'm recording a relatively heavy band and they're using big distorted guitars with a lot of palm muting, a lot of what we tend to think of as chunky guitars, I might actually want to make sure that I've got my microphone relatively close to the guitar cabinet to really exaggerate that low end. Conversely, if I didn't want that response, all I have to do is think about moving the microphone a little farther away. Again, if I'm working with an Omni, I don't have to worry about proximity effect. If I'm working with a directional microphone, I want to think about proximity effect, and I want to think about whether I want to exaggerate that low end or whether I want to go back to the general frequency response that the microphone would have. As you notice from most of our charts, most microphones do tend to roll off as we move into the low end. So sometimes that bass effect, that bass proximity effect, can actually be a nice boost in the low end to get us a little closer to flat or even a little exaggerated beyond that. And here I've got a slide that shows the difference between a microphone in its normal test position, and this upper line that deviates here is the frequency response we get at 1 centimeter. So you can see this is a pretty significant difference. At some of these lower frequencies, we're talking 16, 18 decibels of difference between when the proximity effect kicks in. At its extreme, 1 centimeter is obviously very close to the microphone, and here at its normal test position, which was probably several feet away. So that wraps up our basic intro to microphones for the Intro to Music Tech course. Again, this is not meant to be a definitive study. In fact, this is really just meant to give you a little bit of background. The goal now is to get you to go out and use the microphones that you have access to and to start thinking about and trying different ways to use them. Think about the placement of the microphone, think about the type of the microphone, think about what it's going to excel at, and to start to build up some real-world experience with this. For those of you who are music majors, an application for this is going to be recording things like demo videos, lesson videos, audition tapes, or if you're working with an instructor and for whatever reason you're unable to be in the same room with them at the same time, you may be doing a lesson over video or sending video to them. We want to think about how we use that microphone to try and get the best tone possible that excels in the things that we really want the microphone to pick up while minimizing the artifacts of the things we don't want. And again, sometimes that's going to involve picking the right microphone. Often it really in all situations involves getting that microphone in the right position to capture the sound as good as possible. At this point, you will have the opportunity, hopefully generally in class, if you're on campus for the Intro to Music Tech class, we'll do some in-class demos and you'll get to see some possibilities for how we might think about miking up different instruments, things like that. Obviously, SRT majors, we will go much deeper in future courses over the next couple of years as we really dig into this process. Microphones are one of the most important tools that we use in the world of sound recording, so we'll dig into them quite a bit deeper. Thanks for tuning in, and I'll see you in the next video.